在有个安嘛，安那个，可能我们还有那个人跟他们讲，就是说专门要开始他们错过，讲一下就进。
紧接着进行大会专题演讲。本次演讲主题为 Engineering Medicine Research for Orthopedic Surgery, Osteo Soft Tissue Sarcoma Diagnosis, and Analysis of Uncertainty。有请国立中兴大学蔡志成教授上台为我们介绍今日的讲者。
各位理事还有我们会员，请主任高教授，今天我们很荣幸特别邀请到 Osteo University， 这是在纽约州的，它是纽约州立大学，不过是在纽约的旁边，风光明媚的地方，所以培养出这么好、这么优秀的教授。叶东升老师今天在讲，他也曾经在这里开过。对，那他早年叫做 State University of New York， Stony Brook， 他现在就直接叫 Stony Brook University。然后现在在那边的机械系的高一民教授来跟我们分享一下 Engineering Medicine Research， 也就是说我们现在做机构机器，其实我们大的一块的应用，实际上是用到医学。或者我们叫做生理工程这一块，他刚好也在做这一方面的研究。那么这一次特别邀请到他，当然他也是中兴大学的讲座教授，他也是杰出校友的系，所以他前2天从美国风尘仆仆飞过来，我可能有点紧睡觉，不好意思在这个时段在马里来跟大家分享一下他们做的研究的内容。那我们是不是以热烈的掌声欢迎高教授？
谢谢蔡教授。
这个时间最累，刚刚看到安宁报纸就知道了，有点快要晕船。所以这边现在呢，看到我们话题又来临时了，
对，是有点时差。谢谢蔡教授，也谢谢邀请，然后理事长，还有各位监事、各位同学、各位老师，各位前辈，大家好。我要跟大家分享的是我最近这几年在做的一些 engineering research。那因为这些名词我真的是不晓得中文怎么样讲所以等一下大概就是直接用英文讲的，有问题的话就请你举手问一下。那因为我们在讲说 I'm between your dinner and me， 所以我就不能够讲太久了，希望就是大概40分钟能够结束，或是35到40分钟。所以其中有一个题目我会把它跳过去。我主要就讲那个我们engineering medicine research里面的议题，然后之后呢讲到一个蛮重要的一个 uncertainty propagation。你如果做过那个intended measurement课，你就知道 error propagation。那如果说你是在做用4x4 homogeneous transformation matrix 的时候，你怎么样去那个做这些 uncertainty propagation？我觉得那个题目那个讲题可能跟大家比较有切身关系。好，所以我这边有3 parts。First part vision guided bone sarcoma surgery。sarcoma 就是癌症的那个专有名词在 medical 界。所以 bone sarcoma 有时候叫 Osteo sarcoma， anybody here doesn't understand Mandarin? Okay. So this is the MRI image of distal femur bone. This is distal femur right here, and then you can show the plasma. Okay, so this is an MRI image of a 16-year-old female patient, teenager, who had an osteosarcoma. So the osteosarcoma normally originates somewhere here. Clinically, is almost always here, surrounded by the green lines. And it often happens in child or teenagers. So the previous treatment is amputation. So from here down, if the tumor is here, it will be total amputation right here. So the whole leg is cut. And that fundamentally changes the quality of life of the person, particularly a teenager, forever. So my collaborator, who is attending in orthopedics, when he was doing his residency in Mayo Clinic in Minnesota, he created something like this using a plastic piece machined in machine shop. And that plastic piece would help him to do the resection, to cut away the whole segment here and here and here, and take out all osteosarcoma. All right, so that's good, because after that, we need to put another implant. But remember, this is teenager, their bone continues growing, right? So in about 10 years, you need to take it out and do another implant. But at least it's not total amputation. But the challenge is when you want to take out the bone with osteosarcoma, you better make sure that this has what they call negative margin, so that you cannot cut right here. If you cut right here, the patient is going to die very quickly. So it's easy to see that on this MRI scan, but it's very difficult in all operating room, OR. When you open up the flesh, you look at the bone, you have no idea where this is. Because in MRI you see it, right? But when you open it up, all you see is the bone surface. You actually don't see this osteosarcoma. And that is the biggest challenge. Alright, so we need to take out the tumor with surrounding healthy tissue to make sure that you have, again, negative margin. Negative margin is a term of pathologists. So when they see negative in tumor tissue, then they say that you have negative margin, which is good. Positive margin is not good. Okay, so this is a video that we made. I think it's available in one of the papers that we published, but I'll explain. So in this is a computer model, and here this is osteosarcoma. We need to do resection here. All right. So this is an image in computer, and we create this modular chips. I'll explain that a little bit later. So with that, there's this cross diffusion, and we'll project the lines onto it so that the doctor has some idea. This is the setup, the surgical setup. There will be more images later on. So this is a modular chip that you can assemble right at the OR before you do surgery. This is different from customized chip, which I'll also explain a little bit. And with this is the actual surgery on the cadaver bone. carefully remove the blood vessel, also nerve. And so the whole thing, he was explaining that to us, me and my students, while he is doing this surgery. It took him 30 minutes, and he told me afterwards, because he explained to us, if he does it, it's probably 10 to 15 minutes. You can see that he scrubbed the bone clean, because that's where we are going to identify where the osteosarcoma is. This is a 3D marker that's being pinned down using what's called styrene pin onto the surface. That's a 3D scan of that image when the flesh is open, it's bone. We need about 30 by 30 millimeter area for matching. So the job is to match what you have scanned, what's open in the patient, with respect to the green computer model. Because on the computer model, you know exactly where the osteosarcoma is, right? In OR, you don't know where it is. So after that, this is a 3D marker. After it's registered, then the 2D marker is stepped out. You see that the surgeon is aligning the projected line. And once that's totally aligned, the styrene pin goes in. These are all what you normally see in OR table. They actually use all these treatments. The drill also is part of the OR. We push that down, and you see that the cheek has slot. So this is alignment, but then the cheek has slot, and slot is where the surgical saw goes in. So the surgical saw right here. This is like a saber saw. So it goes in and actually cut the bone away. Now, this is a cadaver bone, so it's not live. But if this is a real bone, you see blood tips coming out. And after that, so you have these two lines resected. So the last one is horizontal line. You change the different cheek, but you already have the reference of styrene pin. So after that whole piece with osteosarcoma is removed with the vector margin. And this will be very accurate because you match what you have in MRI scan or CT scan. And you know exactly what the tumor is. And our system actually reproduces that preoperative plane and project those lines that's called osteotomy lines for surgery. So we use this technology without our equipment. They actually do this by freehand. So they open up the flesh and they look at some features because your human bone still has these joints, right? So there's some anatomical features. So you look at the feature and they use a ruler, actually literally a ruler, and start measuring. And they use a blue pen to mark where they want to use it. This is not accurate. That's why they have to take a latent margin of about 10 millimeters, about this big, because they're not sure where it is. So to be safe, you increase that margin so you can make sure that you will take that cancer away without touching it. Again, if you touch the cancer tissue, then the patient will die without that. So it depends, the traditional freehand method depends on the surgeon training and their skill. You can also produce this patient-specific instrument like 3D printed chips. And we have done that about 10 years ago. And you probably see a lot of paper in this engineering methods and research that use 3D printed chips. I can tell you, 3D printed chips, although it sounds very good, when you are working on bone like femur, there's a lot of ambiguity because femur is largely cylindrical, right? So when you put your 3D customized chip of this patient's anatomy out, there is still play. So you cannot match exactly where you need to. So it still introduces error. So 3D printed chip sound very good, but actually in OR is not that good. and computer-assisted navigation system. This is seems like intuitive Da Vinci robots or other robots. They have high cost. My collaborator once was given the chance to loan such a robot for one day. He was being quoted a price of $250,000 US, so $4 million for one day. So he didn't take it. And not every hospital has that. So what do? We developed this system. So a quick overview of this system. It has this projector and there's a camera. So after you have registered the ball, and we'll talk about that, the camera can track this in real time. Now in OR, the ball can still move. The doctor may be moving there or the patient in anesthesia shouldn't move, but in OR everything moves. So we have this real-time tracking. It refreshes every 1 second. So you are never out of alignment. And then this regular projector will project this osteotomy lines onto the ball. So once that is done, you can actually do freehand resection because you already have reference. Now the problem is if you just look at the line and try to do resection, you can be 90 degrees perpendicular to the surface. That would be ideal. But then sometimes you go in like that, and that's not ideal because you still have a chance of cutting into cancer issues. So instead of those computer-based navigation that you need to look and monitor, do resection, look and monitor, do resection, this is consistent with surgeon's training. So you look at osteotomy lines, you just do the resection. So what we developed is a tool to help orthopedic surgeons to do their job and do their job much better and more accurately. So let's see. The equipment has number one, which is circle in the rock, a structural light scanner. No radiation, it's just a magnetic light scanner. And then a machine vision camera. Number two is 4K camera. And number three is a light projector that projects the osteotomy line right here onto the bone for surgery. And then computer workstation, which is shown here. So our program is all written on a laptop computer. So before the surgery, the surgeon will actually do a preoperative planning. This is before operation. First, you need to acquire the data using either MRI or CT scan. And after that, you have the exact location of the sarcoma. And after that, you generate 3D model on your computer that includes the sarcoma. So from that, you actually plan out how you're going to carry out the resection ideally. So these are called osteotomy lines. Right. So the surgeon in the operative planning would design what are the osteotomy lines in order to remove the entire osteosarcoma. And our system is a system that helps surgeons to reproduce that in OR. Okay. So that's the basic procedure. All right, so the first thing you need to register the bone. So once in OR, once the flesh is open, you see the bone surface. But you still have no idea where the osteosarcoma is. But you do have your preoperative planning. So if you can register the bone that's been opened to your computer model, and if the two has a 99.9% matching, then whatever you plan in the computer model can be reproduced onto the surface of the bone in OR. And by projecting where the osteotomy line is, then you can do surgery. So the first thing is registration. So it has those ridge lines. And then use structural light to do the scanning of the surface of the floor that's being opened up by the surgeon on the OR bed. And we captured that about 30 by 30 millimeter area to match with the computer model. And the system actually identified the marker as part of the board. And then, with all this procedure, the end outcome is registration. So now you have registration of what's being opened in OR that the doctor sees. Also the computer model that has a very precise preoperative position. Alright, so now at this time we put a 2D marker on 3D marker. So we designed that and it's matching. So the 2D approval marker is provided, which is right here. 3D marker is what we saw earlier, and 2D marker is on. And once 2D marker is on, it enables the system to do real-time tracking in 1 second refresh time. So then the real-time tracking, it does, and then it does these things, recognize bone pose as related to the CT scan in computer model, and also compute coordinates of the preoperative osteotomy designs as represented in the system. So this is important. Now, if you look at this, what you see is there are different coordinate transformations. So you have a coordinate frame in the 2D marker, and then you have a coordinate frame in the camera. So there's a 4x4 homogeneous transformation between the two, right? And then from camera to projector, you set up coordinates here. There's another 4x4. And then projector to the osteotomy line to the bone surface, there's another 4x4. So you have at least a 3 4x4, and then also calibration. And that is all computed in our program to produce the projection of osteotomy lines. Alright, so once we have real-time projection, we can do the resection based on the projected osteotomy lines, or we can assemble a modular jig, not customized jig. It's a modular jig, so they can be disassembled and go through autoclave to sterilize and be used for investigations. So it goes into the regular hospital floor. So either manual or guided. And the result is intuitive real-time guidance and having surgeons focus on the surgical field with very high precision. Okay, so these are different view graphs of the experiments of the labor ball. And that is the modular G that guide the orientation of the blade in order to do very effective section. So I can skip a lot of this explanation, but the most important thing is we get accuracy of typically less than 1 millimeter. And that's as good as any published result or any robotic system or any other system that's in the market right now. And even there is blood flow, as long as, so the scanner, the 3D scanners takes about 20 to 25 seconds. So we just have to make sure that within that 20 to 25 seconds, there's no blood coming out, which is possible. Okay. Now, if you're really concerned, you can use impression molding. This is a dental molding material that will get a negative of bone surface, and mathematically it's very easy. Once you get the negative of the surface, you just invert the normal of the surface and become the bone surface. So mathematically it's super simple. And from that, you can also capture the bone geometry. So this is another way of doing registration. We actually try most of them, they come out to be So if you use manual method, is 7 millimeters or 71, which is already better than 10 mechanics, 1 millimeter or less. So these are some of our experimental results. We define different terms here, but you can see that this is nearly 1 order of magnitude smaller than millimeter. Okay, so we apply the same system to pelvic. Now, pelvic dissection is more complicated. Number one, the anatomical geometry is very different. So suppose the sarcoma is right here. You also have slightly more complicated modular G. But the equipment is still the same. You have 3D marker, 2D marker, and then you project the osteotomy lines. There are 4 different types of pelvic dissection. Okay. So there's type 1, type 2, type 3, and type 4. Type 2 is most complicated because type 2 take out the whole socket. So this is where the ball and socket is. So this type 2 take out all socket. And this is typically done in total hip replacement. So we did this, apply the same thing on pelvic. We actually did 3 cuts in this result. You can see that the improvement is also very significant. And this is some of the experimental results with statistical analysis. And you see that freehand methods sometimes actually encroach upon the tumor, but our vision scanning system always keep outside of the tolerance. Okay, so we've done this, and now we are trying to do actual clinical trial. And clinical trial in the U.S. is very complicated, and we show you in Taiwan also. So there's a lot of hoops to jump over, and so we're trying to do this on patients that really need the bone removed from cancer. So before we move on, we'll apply our procedure to drill some holes, so we can do post-surgery 3D scan. So that's ongoing. We're hoping that we'll get appropriate approval to do this. It took a long time. It took at least more than 1 year to get approval process. We're still waiting. All right. So the next is error propagation, and this may be something that you will be more interested in because error propagation, and in this case, we call uncertainty propagation because uncertainty is represented by statistical covariance matrix. So if you have a pole produced by a motor shaft with force F and radius R, and if F, the force has X% of error, and R has Y% of error in measurement, what will be the error of T when you find the measurement? This is very standard problem in mechanical measurements, right? So error propagation equation is very straightforward. You take the natural log of the equation, so it becomes log F plus log R, and you do differentiation, you have dt over T, and that's percentage of T, right? So what it says, this equation says that the percentage of error in the torque, which is product of F and R, is actually the sum of the percentage of error of F and R. And you're probably very familiar with this. So if F has 3% error and R has 4% error, then T has 7% error. Right. Now, what about 4x4 transformation matrix? The 4x4 homogeneous transformation is not as straightforward as this, right? So how do you deal with it? So this is an example of the derivation. So the transformation from coordinate 1 to 3 is the multiplication of 1 to 2 and then 2 to 3. Right? So if you want to know the error or uncertainty produced by this 4x4 continuous, you need to get the two together. But it's not like the natural log and differentiation. You need to represent the transformation matrix uncertainty as represented by covariance matrix, which is 6 by 6 matrix of 1 to 3, is given by this congruence transformation, where these two terms as this congruence transformation plus that, and this Jacobian matrix is defined. For example, J12 is defined as partial x13, partial x12. And since both of them are 6 by 1 vector, so you actually get 6 by 6 matrix. So this is the equation, and the proof is also in dissipation of kinetic DOT dissipation. But this is how it came about. So if you know the covariance of 1 and 2 by this homogeneous transformation, you can find the covariance of x1. So this equation becomes very important. Now the Jacobian matrix purely depends on x, y, z, and simply any of the coordinates. So quantifying the uncertainty in tracking. So quantifying the uncertainty of our system with possible registration error, tracking error, and calibration error. So this all will be introducing uncertainty to your system, right? So if you can calculate the uncertainty propagation based on that congruent equation, then you'll be able to know from your system, if you know that your measurement, for example, the 3D standard measurement, has an error of 0.05 millimeters, that will give you the initial covariance, right? And then you use a congruence transformation, you'll be able to get the uncertainty in the next stage, So that congruence transformation equation is very important because that's the only known way to quantify uncertainty or errors whenever you use 4x4. And in kinematics and machine learning, you always use 4x4. And so that's how you do the uncertainty propagation. So in our system, again, we have the 2D marker, and then from that is coordinate frame N to camera, and camera to projector. Projector then to your bone surface for resection. So with these frames, you look at this cascaded transformation. So ideally, if you know everything, then it is just the sum of the three transformations, congruence transformation. So that will give you an idea of what your uncertainty here in your osteotomy lines based on your tracking, your registration, and your calibration. And so that's one part. And the other part is once you have projected this, you need to do resection, right? So resection is into the screen, and that produces a plane. The osteotomy lines becomes a plane, and that plane also has its own uncertainty. And it turns out that the uncertainty of the plane can also be quantified. But the plane has only 3 degrees of freedom. The covariance matrix that we talk about is that 4x4 homogeneous has 4 degrees of freedom, right? 3 translation, 3 linear. But a plane only has 3 degrees of freedom. Equation is ax plus by plus cz plus d is equal to 0, right? So your a, b, c, d, but really, you only have 3 degrees of freedom. It's two translation and 1 rotation. And the equation to quantify that is like this, where these are coefficients of the plane, ax plus by plus cz plus d is equal to 0. And your transformation p to I that we obtained earlier, which is 6 by 6 matrix, and this is 4 by. This is a transformation between p and a vector in the I frame So the Jacobian is partial P or partial XPI. So Jacobian actually becomes a 4/6 matrix. And at the end, you use one congruent transformation between these equations, and you can find out the uncertainty of the plane. So this is what we did on the 2D marker. We actually use a microscope to see. This is printed by 600 dpi laser printer. I don't know whether you have seen it before on the microscope. It's actually not 90 degrees straight edge. There are actually a lot of tonal dust outside of this boundary. So those tonal dust give you uncertainty already. And the uncertainty actually can propagate through the whole thing. And this is the work that we've done earlier, maybe 4 years ago, using Monte Carlo simulation. And if you are working on this service matching and ICP algorithm, you probably will recognize this mathematical equation. And that gives you ability to find covariance matrices. And of course, these are the Jacobian matrices. It's messy, but it can be done. And using MATLAB code or mathematical code, you can actually calculate this. And this is our recent result on pelvis. You can see that the maximum distance deviation, that's the maximum difference between your target plane and your actual plane, is limited within a very reasonable range. So that's uncertainty propagation. And so before I look into this, I actually did not know how to do the uncertainty propagation. But once we discovered this, the uncertainty propagation, anytime you use 4x4 homogeneous transformation, the congruent transformation is the way to go. And it becomes a stochastic methodology because you need to deal with that 6x6 covariance matrix. Right, so I'm at my 40-minute mark. So number 3, I'm not going to talk about too much. So the motivation is that once you have the cancer removed, you want to find out if the tissue that is in the healthy part of the body still has cancer related, right? So a way to do that is using the Raman spectrum to do that. And we have a handheld Raman. So I'm going to just talk about this is typical Raman spectrum of fat and muscle, which is skin, part of the skin, and humor. They look different, but it is actually not that straightforward. Even when they look differently, when you scan fat here, they all come out to be slightly different. So this is how we prepare a sample. This is called pathologists scan sample, and then they look at this under the microscope. The pathologists will tell us, look at this area that you mark like that. So then he will prepare us a sample without scan, and then we'll find out the spectrum approach. This is our recent study, which was published in the PLOS One, an open journal. We also published our data set. Now, in this machine learning AI system, the data set is actually the most important problem. And we spend a lot of money to collect those data. But we give the data freely to everybody who wants to use our data so they can conduct their experiments and apply their AI model to do things like these are the spectral signature of typical Raman. This is called wave number. In biological sample, it's typically 400 to 1800. You can see this carbon double bond, this CH2 bond, and this single carbon bond. This carotenoid, and this amino acid, and nucleotide. So the different peaks mean something different. The more important thing is here. We introduce a term called clinical alert. This is in your is classified as benign or normal. So you actually have cancer, but your AI system tells you that it's okay, it's not cancer. And that will trigger clinical alert because this is not the case that you want to get past. If you don't have cancer and the system qualify you as having cancer, that's fine because then you go to see doctor. But if you actually have cancer and the system tells you, no, you are free, you have no cancer, then you're really dangerous. So these are some of the results. I won't go through that, we're running out of time. And this is a confusion matrix. After we did this by AI. And these are the data that was available for everybody. It's open source data. Okay, so that's the end of my talk. Credit given to my PhD students and my collaborators from medical school. And that's the end of my talk. Thank you.
感谢高教授为我们带来精彩且专业的演讲。高教授，请留步。接下来我们要颁发感谢状，感谢高一鸣教授精彩且深度的演讲分享，让所有会员在学术研究及职业发展上有所启发，收获良多。本会特别颁发感谢状，以资感谢，再度有请。